Hi guys, welcome to another video. The topic of this video is maximum likelihood estimation, or better known as MLE. If you, like me, are from a non-core math or a non-core stats background and are into data science or machine learning or predictive analytics, you may have felt a little clueless or maybe even a little intimidated on hearing terms like likelihood or log likelihood or negative log likelihood. In my view, the best way, maybe I should not say the best way, but an effective way to understand these terms is to understand them in terms of an example in Excel, where you can play around with the different values or inputs and see the different outputs. So let's jump in. There is a coin. Well, there is somehow always a coin in probability examples, and this example is no exception. And what I need to find out is the probability that this coin lands on heads in any given coin toss, the probability of heads for this coin. And I'm going to call that value P, small p. In order to find out this value of small p, I toss the coin 40 times, out of which I get 19 heads and 21 tails. I can use this data to simply divide the number of heads by the total number of tosses and say that the probability of getting heads is 48%. That is one way. The other way to do this calculation is to use the maximum likelihood estimation method, which is as follows. For the value of p that I'm interested to find out, I take all the possible values that it can take. And since it's a probability, it can range from 0% to 100%. So, well, I don't take all the values of p, but I take the values of p from 0% to 100% in increments of 2%. So, 0%, 2%, 4%, 6%, and all the way down to 100%. There you can see the last row is 100%. Let me come back up. For each of these values of p, I then calculate the probability, or what I will call the likelihood now, of observing my data, of observing 19 heads and 40 tosses. To compute the likelihood, I use the binomial formula. The description of the binomial formula is given on the left. If you want to remind yourself of what it is, you can pause the video and have a look at it. I have implemented the binomial formula for the first two values that p can take over here and here, and it is implemented for the remaining values of p in the same way. What we observe from this data is that when the probability of getting heads in a single coin toss is low, in the range of 0% to 10%, the probability of getting 19 heads and 40 tosses is also very low. However, as I inch towards higher values that p can take, somewhere in the range of 32 to 40%, I observe that the likelihood of getting 19 heads and 40 tosses also rises higher and higher. And at p equal to 48%, that is when the probability of getting heads in a single coin toss is 48%, I observe that the likelihood of getting 19 heads in 40 tosses is also the highest. At 50%, it's 11.9%, and at 46%, the likelihood is 12.3%. So it maxes out at 12.5%. That is, the likelihood of getting 19 heads in 40 tosses is 12.5% when we assume that the probability of getting heads in a single coin toss is 48%. So as per the maximum likelihood estimation technique, we have got the value of p equal to 48% as an answer, which is the same as what we would have got if we divide the number of heads by the total number of tosses. So a natural question to ask is, why go through this whole process of computing the likelihood for all probabilities and find out the probability at which the likelihood is maximized instead of just doing a simple division? And that's a valid question to ask. There are two answers to that question. The first is that I have chosen a very simple example to be able to convey the idea of maximum likelihood estimation. In practice, maximum likelihood estimation is used in more complex situations where doing a simple division is not one of the ways to arrive at the parameter estimate. The second reason for using the maximum likelihood estimation method is that it allows me to calculate the relative likelihoods for different values of p. So for example, if I divide the likelihood at p equal to 44 with the likelihood at p equal to 56, I get 1.62. Now I can make a statement like, given the data, that is 19 heads out of 40 tosses, it is 1.62 times more likely that the probability of heads for this coin is 44% than the probability of heads for this coin being 56%. I cannot make such a statement or a deduction if I use the division method to find out the probability of heads for this coin. And statements like this are used in Bayesian statistics where the probabilities need to be updated in the presence of given data. Finally, I just want to make a remark about the advantages of doing all this in Excel is that once you have plugged in all your formulas appropriately, for example, the formulas in these cells and the formulas over here, then you can just play around. So let's say, for example, in 40 tosses, instead of 19 heads, what you get is 15 heads. And now you want to see what is the parameter estimate as per the maximum likelihood estimation technique. So you can see that instead of p equal to 48%, now our likelihood maxes out at p equal to 38%. For p equal to 36%, it's 12.7%. For p equal to 40%, the likelihood is 12.3%. And at p equal to 38%, the likelihood is 12.9%. So that's how our answer changes. And so do our inferences about relative likelihoods. So if you remember, this value earlier was 1.62 and it has changed to 11.15, which means that the likelihood of the probability of heads for this coin being 44% is now 11.15 times more than the likelihood of the probability of heads for this coin being 56%. So that sums up the explanation for maximum likelihood estimation technique. I hope you found it useful. Give it a thumbs up if you liked it. Share it with people with whom you think it might be useful. And if you find it worth it, then subscribe. Thanks for your time. Bye bye.